In this lesson, I'm addressing the challenge of rearranging an integer array nums such that all zeros are shifted to the end while preserving the order of non-zero elements. This problem is common in scenarios where data needs to be cleaned or organized efficiently. The solution needs to be implemented in place, meaning I modified the original array without using additional memory, making it suitable for memory-constrained environments. To achieve this transformation, I'll use a strategic two-pointer technique. This approach optimizes the process by minimizing unnecessary operations and ensuring efficient traversal through the array. The two-pointer technique is especially useful in array manipulation problems because it allows me to manage multiple conditions simultaneously with minimal overhead. If I was to describe the steps needed to solve this problem, I would first initialize an integer, which I called non-zero, to 0. Then, after relocating all the non-zero values, I fill the rest of the array where there are empty slots with zeros. This function is of type void, meaning it doesn't return anything. So, let's take the steps one at a time. First, I need to initialize my variables. As I mentioned before, I have a non-zero integer which equals 0. This pointer serves as my tracker for the next position where a non-zero element should be placed within the array. By maintaining this pointer, I can effectively manage the placement of non-zero elements without disrupting their relative order. Next, I do my first iteration. This first iteration moves the non-zero elements on the position indicated by non-zero. When the algorithm encounters a non-zero element at index I, it copies that value to the position indicated by non-zero, and then it increments non-zero. My for loop effectively shifts all non-zero elements to the beginning of the array while maintaining their original relative order. To better comprehend the idea, let's consider an example where the array nums equals 0, 1, 0, 3, 12. Initially, non-zero equals 0. At I equals 1, nums of 1 equals 1, non-zero, so I move nums of 1 to nums of 0 and increment non-zero to 1. At I equals 3, nums of 3 equals 3, non-zero, so I move nums of 3 to nums of 1 and increment non-zero to 2. At I equals 4, nums of 4 equals 12, again non-zero, so I move nums of 4 to nums of 2 and increment non-zero to 3. After this pass, the array looks like 1, 3, 12, 3, 12. Once all non-zero elements have been relocated to the front of the array, the next task is to ensure that the remaining positions in nums are filled with zeros. To accomplish this, I initiate a secondary loop starting from the index non-zero. Within this loop, I iterate through the remaining indices of nums and explicitly assign each element the value of 0. This step guarantees that all zeros are pushed to the end of the array after the non-zero elements. Continuing from my example, starting at the non-zero equals 3, I set nums of 3 and nums of 4 to 0. The final array becomes 1, 3, 12, 0, 0. By leveraging this two-pointer technique, I optimize the algorithm's performance with a linear time complexity of O(n), where n denotes the number of elements in nums. This efficiency is achieved by traversing the array a minimal number of times and ensuring that each element is processed exactly once. To conclude, the two-pointer technique effectively addresses the problem of moving zeros to the end of an array while preserving the order of non-zero elements. This approach is efficient, easy to implement, and adheres to the constraints of in-place modification and constant extra space. By understanding and applying this technique, I can solve a wide range of array manipulation problems efficiently and elegantly. And now, let's run the code to ensure that everything works properly before I submit.